Can you hear me? Okay. First of all, I'd like to thank the organizer for inviting me to this conference in ICTS. So today I'll talk about the topological defect and in biological active matter. And these are my collaborators, and Kawaguchi and Nishiguchi. Both are former students. Now one is in Harvard, the other is in Sakurai. Kagama is a biologist in Kyoto University, and Higushate is in Sakurai. By the way, this is a nematic order at the scrambled crossroad in Shibuya in Tokyo. So you already know the lot about active matter. There are a lot of introduction about active matter. In our lab, we do experiment on active matter, asking several questions. So for instance, what is the mechanism of the self-propulsion? And what is the general theory? Is there any general theory for active matter? And also interested in the different state in phase in active matter, and topological defect, and the turbulence, and disorder, laminar turbulence transition. And we are also interested in the biological function of the active matter system. So, okay, this is an example of what we are doing in our lab. We study the self-propelled Janus particle, and we study the microtubule kinesin motility assay. Also, we study the swimming of Filamentous bacteria and the culture of neural stem cell. Okay, today I talk about this swimming bacteria and the neural stem cell cultures. So the physicists are interested in the order and disorder transition. However, in the two-dimensional system, there is a Wagner theorem. It says that if there is a continuous symmetry and a spontaneous breaking of symmetry at final temperature is not allowed for sufficiently short-range interaction systems in 2D. And because this is due to the nucleation of the presence of the topological defect in the two-dimensional system, it's so easy to excite pair of topological defect. And in fact, this was pointed out many years ago, and they got Nobel Prize last year. And however, in the active matter system, the long-range order in 2 dimensions has been predicted by a Vicsek model. And Vicsek model is, I think many people know, so I don't need to explain in detail. Here we don't have a lattice. Each particle moves with constant velocity, and their orientation is determined by averaging neighboring particles. And there is a thermal noise. And since the particle can move, the effective interaction range is longer than the lattice system. So they observed the long-range order in Vicsek model. And people also found many other systems having different symmetry. For instance, a particle can be polar or apolar. Apolar means a particle can change the direction of motion stochastically, for instance. Although alignment interaction can be polar or nematic. So as a simplest classification, we can classify the active matter system whether motion is polar or apolar, or whether the alignment is polar or nematic. And the Vicsek model corresponds to this case. And in our Janus particle, it's maybe belong to this case. And the Filamentous bacteria shows the nematic alignment. but each bacteria has a polar symmetry. It has a head and tail. And molecular motor and motility assay also belong to this. And I don't know this case is published or not, but Benoit and Chate are studying these very special cases. And today I spend most of the time about this case when the particle change direction motion stochastically. So motion is apolar and alignment is nematic. In fact, this case was studied many years ago by Narayan and Ramaswamy for the shaken granular rod. And today I talk about the biological example of this case. So this is the paper by Narayan, Ramaswamy Menon, and they use the long rod shaken vertically. And when they increase the density, they observe the nematic order. And in fact, they also observe a topological defect in this nematically ordered system. And they also found the giant number fluctuation. Giant number fluctuation is if you measure the density, standard deviation of density by changing the measuring area. If you increase the L, N, and for the normal system, this alpha should be 1/2. However, the giant number fluctuation predict this is larger than 1/2. However, after this experiment, many experiments have been done, have been measured the giant number fluctuation, but all the experiments measure the giant number fluctuation in the swarming phase, not in the ordered phase. The original prediction, theoretical prediction by Ramaswamy and the Tonatu was the giant number fluctuation in long-range ordered phase. And maybe I don't need to mention about the topological defect. It's already described by Yeomans. And we can define the topological charge in the nematic system. We can have half-integer topological defect. This is just an example of the topological defect, visualizing topological defect in the liquid crystal, nematic liquid crystal. So in the quenching state, we can see the annihilation of topological defect. But in this case, most of case, the topological charge are +1/2 or -1/2 topological defect on the right-hand side. Because the elastic energy is smaller for the smaller topological integer topological defect. So I just want to mention that there may be some difference in active matter. For instance, if we have a +1 topological defect in active matter system, like this, and if the interaction is nematic, the outgoing particle can easily escape, and only the inward going particle can stay. So it makes aster +1 topological defect. And also this topological defect can be observed when the steric interaction is strong enough. If the particle can pass each other, like in Vicsek model, this state also never be observed. It can disappear very quickly. And in the system with steric interaction, we can expect to observe a topological defect, and especially in nematic active matter, active nematic system, we expect +1/2 or -1/2 topological defect. Because this is a signature of the nematic system. In a polar system, we cannot expect this half-integer topological defect. So this is a possible lowest order topological charge expected in the different active matter system. And in Vicsek model, we don't expect the topological defect because the point in Vicsek model is just a point without excluded volume interaction, no steric interaction. However, if you introduce some steric interaction and if you confine in some sphere on the square with reflecting boundary or strip boundary, then due to some topological constraint, we can expect topological defect or domain wall. Also, if we can also consider higher topological charge, although it consumes more elastic energy, but we can expect aster vortex even in these systems. Okay, now I explain about the experiment on Filamentous bacteria. Here we use bacteria as a polar element, filament. And we use a very special long filamentous bacteria. So they have nematic interaction. So we inhibit cell division by using antibody, and then the normal E. coli can elongate up to 20 micrometer, for instance. Then also we use a mutant which cannot tumble. So they move only straight in their head directions. And we use PDMS and push this PDMS very strongly. Then finally the gap between PDMS and glass plate become order of 2 micrometer. And so we observe a large area. Okay. And this is a photo for the fluorescent bacteria. And for low density, at low density, of course, there is no ordered state. And as we increase the density, and we start to see something interesting. However, if the gap between the PDMS and the glass plate is large, the interaction is weak. So we still observe disordered state. And when the gap becomes very narrow, 2 micrometer, they start to collide and interact. But however, they can also pass each other, crossover. Then we start to see some alignment. And maybe you see some orientational order in horizontal direction. And we can track each bacteria and make the statics of collision. So we found many cases bacteria can pass each other. They don't interact much, but they weakly interact. And this is an inward angle difference, and this is an outward difference in angle. And there is symmetry, nematic alignment interaction can be seen in this plot. However, also you see this effect is very weak, and there are a lot of scatters, and in many cases, particles can pass each other. And however, this weak interaction is enough to show the nematic order. So we can track each particle, and so we did analysis. So this is, for instance, the observed ordered state. So you see the bacteria are passing each other. They are aligned nematically, and they show the long range, kind of long range order. We don't see the very clear topological defect because the steric interaction is very weak. And even at high density, we can visualize. Here we visualize only fewer bacteria by using fluorescent bacteria, E. coli. Only 20% of E. coli are fluorescent level. And you see some orientational order. And even at lower magnification, there are some vertical motion. You see there are upgoing bacteria and downgoing bacteria. There are many bacteria, but however, you cannot see all the bacteria. Okay, so we analyze this data by using image intensity. To determine the orientation of the bacteria, we use a structure tensor method. Structure tensor method is just use image intensity and calculate the gradient in x and y direction. They calculate this eigenvalue and eigenvector of this structure tensor, and which gives the steepest and the least steepest direction by the eigenvector. So from this, the largest eigenvalue and the minimum eigenvalue, we can define some kind of correlation or coherence, orientational order. So this parameter decays in disordered state in proportion to the 1 over square root of square. Square means the total number of bacteria. So this is a normal fluctuation and disordered state. And for the ordered state, this coherence ordered parameter seem to saturate. So here we plot this curve by expanding the vertical axis. It seems this order parameter saturate. So saturate to some finite value. So we fitted this curve by constant plus power law decay. And so if this fitting is good, we can say that this order parameter does not decay and saturate and decay to some finite value with power law decay. So this is some kind of long-range order observed in this system. So we try to measure giant number fluctuation in this system, and we normalize standard deviation of the number fluctuation and normalize by square root of n. And for disordered state, this should become constant. However, for ordered state, the exponent is small. It's 0.63. However, it's evident that this is clearly deviated from the constant, the normal fluctuation. So there is the giant number fluctuation in ordered state in this filamentous bacteria system. Okay. So here, from now, I want to explain about the experiment on neural stem cell. In this case, yes? 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 Okay. Oh, okay. In your granular system, it's not like that. Okay, okay. Okay. This is because this is polar. Yes, yes, okay, you're right. Yeah. Yes. And the next system is motion is apolar. And the cell moves back and forth, and then alignment are nematic. So I talk about the neural stem cell. So the neural stem cell can be made from embryo stem cell, And under some environment, neural stem cell can differentiate into neuron, astrocyte, oligodendrocyte. However, in other specific conditions, we can keep this neural stem cell state for many, many months, for instance. And we can store this cell in the refrigerator and melt salt for every use. So this is a very good system for experimentalists. We don't need to kill mouse every day. So they can divide in number, divide in 24 hours and grow in number. And this is very, once you know how to make culture, it's very useful system to study. In the real brain, the brain, for instance, our mammal brain consists of 6 layers in cortex. And in development stage, the neural stem cell makes some polar order in the thin layer. And from apical to basal direction, each cell makes elongated attachment shapes. And the nucleus can move up and down depending on cell cycle. They divide into 2 at the apical, at the bottom, then start to move upward, then again going back to downward. This is called elevator motion. And during this cell division, they differentiate and finally makes 6 layers. And it is known that with some specific conditions, the neural stem cell can make 2D monolayers culture. So this is basic characteristics of the neural stem cell. So cell size is about 10 or 20 micrometer width, and the length is 50 to 70 micrometer. So it's elongated. And the cell doubling time is about 1 day. And the cell moves along the elongated axis persistently, but it reverses its direction stochastically. The reversal time is between 1 and 3 hours. And the cell velocity is about 100 micrometer per hour. The observed area can become very large by using some tiling technique. And so in this system, we can observe nematic order as long as 1 micrometer, but we have a lot of topological defect. And if we confine this system into 1D, then we can have longer orientational order. So let's start from the low magnification. So at low density, the cell moves randomly. Left-hand side is a phase contrast image. Right-hand side is a fluorescent image. This shows the motion of the nucleus marked by M. Cherry. And so cell divide, and doubling time is about 1 day. And so density, when the density becomes high, and we see more ordered state. The interesting thing is the neural stem cell can glide and pass each other, even at very high density. There seems no contact inhibition of motion. So they keep moving, even at high density. So this is very maybe interesting property for the neural system. So if you have this nematic alignment and the active nematic behavior, the cell can move past each other, even in the very confined, confluent environment. And however, in other cases, most of the cases in the development phase, the cell usually makes polar order. For instance, this is a movie I got from Professor Ueno in Basic Biology Institute. So this is a movie of the seed taken from egg of the xenopath frog. The collection of cells moves, each cell moves collectively toward some chemical gradient. In that case, the cell can make only collective flocking motion or vortex-like motion. However, in the neural stem cell case, they can pass each other, cross each other, even at high density. That is a very important property. And maybe it is useful, and it can be explained by this. In a adult brain of the rodent, mouse, and rabbit, it is known that there is the motion of the stem cell, progenitor cells from this region to the olfactory bulb. So olfactory bulb, the neurons are constantly renewed. So it is known that there is a constant flow along this long tube. And if we carefully read the paper and look at the movie in the previous study, the motion is nematically ordered. There is a flow along in this direction. At the same time, we can observe the flow in opposite direction. So this kind of stream motion is called rostral migratory stream in biology. And it is known that neural cell adhesion molecule are playing some important role in this system. To mimic this kind of motion, we made a narrow strip, not narrow strip, we made a scratch on the dishes. And if we may scratch two scratch line, then the cells start to move along this line. They cannot escape from this channel. So they are forced to move in a horizontal direction in this movie. So you see there are cells are moving to the right and to the left, and you see the nematic order. This color shows the directional order, or direction of the motion. And here I show the trace of each cells in the low density state. The motion is almost random at the low density. At high density, however, the motion are ordered in one direction. So in this case, they are moving mostly in horizontal directions. And we can show that by measuring the autocorrelation function of the directions. For instance, if we calculate the cosine delta theta for the velocity, and the correlation function, or as a function of time interval, tau, and there's a quick decay, exponential decay, and the characteristic time depends on the cell cycle. It's about 1 to 3 hours. So it's constantly changing the direction of motion. However, if we calculate the cosine 2 delta theta, means if we take the average direction and measure the angle from this x-axis to the moving direction, this delta theta has some nematic symmetry. So cosine delta theta, cosine 2 delta theta doesn't decay but saturate. It means that the orientation is changing along these ordered directions. And this is a larger view. So you see there are some elongated shape of the cells. And you start to see some accumulation of the cell at several points. On the right-hand side, it's a simultaneous visualization of the motion of nucleus by using M-cherry. Motion of cell toward this mound, also you see the flow opposite to this direction. And we can use the same kind of technique to determine the orientational vector, and by using structure tensor, and by just using image intensity analysis, image analysis, we can also track the motion of nucleus and measure the velocity field. So velocity field gives almost the same result for the orientational order. So we calculate the orientation by this method and showed in color. So color shows the angle of the orientation, and here we have a topological defect. This is a singular point, and these are topological defects. And if we look at topological defect carefully, we found a +1/2 topological defect and a -1/2 topological defect. And so this shows the dynamics of cell density at the topological defect. You notice that the density at the core of +1/2 topological defect increase when the density increase. For instance, we observe the motion of the +1/2 topological defect in this direction, toward this direction. And for the -1/2 defect, if it's isolated, this -1/2 defect does not move very much. However, if we have a pair of +1/2 and -1/2 topological defect in a shorter distance, there is an attraction and pair annihilation. In this case, both defect moves. And here we calculate the orientational director field. On the right-hand side, we measure the mean velocity around the defect by using several samples. And here we average the velocity inside a small area and average in time and space. And we see so cells are moving in both directions. Also, the cell change the direction motion from time to time. However, there is a net motion. There is an average velocity toward the core of the topological defect. On this side, there is not much flow. So there is a mean net flow toward the core of +1/2 topological defect. And in the case of -1/2 topological defect, flow fields are almost symmetric because of, say, threefold symmetry. There are no clear net flow toward the core. And here we measure the relative density, cell density around the topological defect. This color shows the time evolution. At early stage, this is almost uniform. But as time goes by, the density increases, but we normalize by the surrounding area. And cell density at the +1/2 topological defect increases in time. On the other hand, cell density at the -1/2 topological defect decrease in time. And this is the growth rate of the density around the topological defect. And to describe this phenomenon, we use a very simple modeling of the active matter, dry active matter. So we use the Ramaswamy's paper on dry active matter on the shaken granular rod, I think. In this case, no fluid, there's no momentum conservation. We neglect mass conservation. We neglect all the inertial term or something, noise. We just remain the active force term and viscous drag force term. And the Q is a nematic order tensor, and the theta is the parameter, active parameter. If theta is positive, the system is extensor. If theta is negative, system is contractile. Here, gamma, we suppose this gamma can be tensor. It means that the friction, effective friction for the cell is different in the parallel direction or perpendicular to the elongated direction. If we assume the gamma perpendicular to this elongated direction is larger than the gamma parallel, then we always obtain that this particle accumulate at this core of the topological defect. So we did a very simple numerical simulation by assuming a very simplest profile of the topological defect, and we have to assume the profile of the envelope of the amplitude S, and we did without doing a numerical simulation, we can estimate how the total density around the curve defect increase or decrease depending on the sign of the coefficient. Then we found the density increase at +1/2 defect and decrease at -1/2 defect. And this is qualitatively agree with the experiment. However, this is just a numerical simulation. The quantitative behavior for the near the topological defect is not so good agreement with the experiment. And there's also we study also biological meaning of this system. The cell adhesivity to the substrate plays very important role. And the laminin is the very important molecule, protein to attach to the other cell or substrate. So we can change the laminin concentration. For low laminin concentration, cell cannot adhere on the surface, and they make aggregate. And if we knock out if we prohibit microtubule polymerization, then the cell cannot be elongated. So they don't have nematic order, and there's no order state in without microtubule polymerization. Also, if we knock down the N-cam, and we don't see the orientation order, we start to see the clusters. And the possible meaning, biological implication of this kind of phenomena of the topological defect in nematic order can be found in the rostral migration stream of the adult rat mouse. And also, maybe if you look at the development stage carefully, for instance, neural tube formation, the cells are elongated and making some order structure. And here we can see the +1/2 topological defect. One of these become forebrain at a later stage. And we can also find some example in which topological defect is playing some role in biological systems. This is a picture of the plants. And near the meristem of the plant, there is a topological defect, but around this stem, there is always orientational order by microtube organization. There is a azimuthal direction. Microtubules are oriented in azimuthal direction. However, at the tip, the direction is not determined. So this is a +1 defect. And to make the new sprout, the new tip appears, the topological charge has to be conserved. In that case, the 2 -1/2 topological defect appears simultaneously with the appearance of the +1 topological defect at this new stems. So this kind of the dynamics related to the topological defect in active matter may be playing some role in the development stage of the biological system. Okay, this is a summary of my talk. So I describe the orientational order in filamentous bacteria and giant number fluctuation observed in kind of long-range order state. And in neural stem cell, we analyze nematically interacting active matter system. And we found the cell accumulate at the core of the +1/2 topological defect and the escape from the -1/2 topological defect. And the accumulation and dilution can be described by a simple theory of active matter. Okay, thank you very much.
Questions?
I had 2 questions. First of all, that when you go to higher densities, you get the nematic state. But what happens if you go to even higher densities?
Okay. In this Kawaguchi's measurement, he mostly took the movie for 1 day. So at that time, we didn't know the long-term behavior. Now we are taking much longer movie, up to 5 days or one week. They still arrive and they still move and pass each other and make mound. And maybe we start to see the double layer or multi-layer. And then we start with some kind of wave propagation. They are now interacting. They can move past each other, but still they interact more elastically.
Yeah.
In that this medium density or not very high density, we don't see such kind of elastic behavior.
Sort of strange that they're moving past each other, because normally you get laning when you have that sort of setup.
Laning.
Yeah. And do you see any evidence of laning?
We don't see the laning. But so this maybe depends on the interaction between cells. So we still don't know whether they stick each other head and tail, or they, of course, on the side they can pass each other. There's not much adhesion, and it seems not much adhesion between head and tail. So they are not following the other cells. So if you don't follow the front cell, the lane formation, you cannot expect lane formation if you don't follow if you don't have a leader and a follower, you don't see the lane formation.
I had one question. You showed the cells accumulating at the +1/2 defect. Did they actually sort of deform in the third direction later on?
Deform what?
Do the cells protrude out of the plane, or do they still stay planar?
Oh, they become 3D, and they still alive. And if you take this mound to make a new culture, they still make the monolayer again. So they are not differentiated. So it's different from the Radu and Yeoman's experiment.
Hello? Yeah. The fact that these cells can glide past each other and move in opposite directions, does that mean that if you wrote down a theory including a velocity field, the coefficient that you might normally call a viscosity is somehow precisely zero, or is it negative? I mean, how is it a system that wants gradients, or is it a system that doesn't care one way or another?
Yeah. This is a good question. In fact, someone asked a similar question. To answer this question, we have to measure the relative velocity between cells when they are moving in the same direction or when they are moving in opposite direction. We are now starting to measure this kind of statistics.
Yeah, I was wondering, could one possibly measure forces rather than measuring? That is, is there a tweezer experiment or something where you can try to see how much work it takes to keep them from moving past or something like that? I don't know.
Yeah. In fact, we did a traction force measurement for Dicty cell, but we also trying to measure traction force in this system because, but the force is very weak, and now we have very soft gels, and we are now trying. And so if the system is extensor, it means that traction force should be going outward. But I don't know the example of that such kind of biological cell. In the cloning cell on the substrate, in most of the case, all the case, the cells are contracting, even in elongated state. So I don't know the force field. Also for the nematics alignment case, I cannot imagine how this traction force field. But we have some very early evidence that the average stress field around the topological defect is stronger than the other places.
Is there no signaling here, or is it? I'm wondering. I mean, is there any effect of signaling between the cells that is not being captured?
This we don't know. Maybe not much signaling.
Particularly in the neural tube, there is definitely a lot of signaling going on. It's not just the mechanics.
Signaling. I mean, there's some chemotactic.
Yeah,
No, I don't think so.
In the neural tube.
In the neuron cell. Yeah.
I see.
I don't think so.
Other questions? So if not, let's connect the speaker.